Hello everyone. Today we will study the 1D heat equation. So, this is a equation given by ut equal to a square u x x. Again t is positive, x is in real line, and an initial value g of x. So, here a is positive, a constant. So, physically this represents the evolution of temperature in an infinite rod. So, though not physically meaningful, but we will see that just like wave equation, this also helps us in analyzing later the temperature evolution in a finite rod. So, before we go further, few historical remarks. So, this equation first appears in the work of Joseph Fourier, a French scientist. So, somewhere in the beginning of 19th century. Okay, there he derives this equation using Newton's law of cooling. So, most of the things we study now, like Fourier series, Fourier transform, they all appear in this work, and this is called, it is in French. So, let me just write it, theory analytic this is in French, the law Chalut. So, simply translated, this is analytic theory of heat. So, whatever Fourier did in this work, it influenced a lot, especially in the 19th century, mathematical physicists, mathematicians. So, and in fact, now there is a separate branch called harmonic analysis, which originated in this work of Fourier. So, he was also successful in deciding to construct cellars to escape extreme weathers. So, in extreme cold conditions would like to remain warm, and in extreme heat conditions would like to remain somewhat cool. So, he was successful in determining. So, remember this is in 19th century, okay, this is in 19th century. So, of course, now we have air conditioners, heaters and what not, but in those, so this is more than 200 years. So, he was successful in determining the depth at which cellars must be constructed in order to escape extreme weathers. Okay. So, and there he exploited the linearity of this heat equation and this linear superimposition that we are aware of now, but it in this work he, so there will be temperature variation, daily temperature variations and yearly temperature variations. So, he took all that into account and successfully arrived at the depth at which a cellar must be constructed. So, a brief account of this, I will give a reference. So, you can just, there is a book by T.W. Corner, title is Fourier Analysis. So, we will also find a good account of Fourier series, Fourier transform, okay, which we are not covering in this course. So, this is published by Cambridge University Press. No, there are many books. Okay. So, I am just mentioning one. So, today what we will do is this try to find a formula for the solution again in the Fourier spirit. Okay. So, before going further let me mention one thing about this heat equation. So, it is a prototype of parabolic equation. So, it has only one real characteristic. Okay. Has only one family. When I say one, and you can easily see that these characteristics the characteristic family are given by characteristic family T equal to constant. And remember, we are prescribing initial condition at t equal to 0, though physically meaningful. So, at some t equal to 0 initial time, you prescribe the temperature in a rod and then you see how it evolves, okay, though physically meaningful. But as far as mathematics is concerned, so what we are dealing here is, so characteristic initial value problem. So, I just stress this thing. Characteristic initial value problem. because we are prescribing the initial values on a characteristic. T equal to 0 is also characteristic. So, and mathematically such characteristic initial value problem they may fail. So, there are three things we should be interested: existence of a solution, and then uniqueness. This is again important as far as the physics is concerned. Uniqueness, and then the continuous dependence. On the initial value. So, together they are known as Hadmar's well posed conditions initial data. So, when we are dealing with characteristic initial value problem, there could be problem with any of these three things, 1 or 2. Okay. So, that means, so even for existence or uniqueness, some additional conditions may be prescribed. So, some additional hypothesis may be required. So, in fact, there is no uniqueness in general, okay. But if you restrict the initial value to certain class, then there is uniqueness. As you see, existence will be there. Again, this continuous dependence on the initial data is there only if you restrict the initial data to a certain class. So, it is very difficult to do all these things in this set of lectures. So, we will just concentrate on certain things, but this is an important equation which makes its appearance in several branches of mathematics. So, and it is also a typical parabolic equation, and it has many properties, interesting properties. Some of them we will be discussing. Okay. So, first we will obtain some spatial solutions. Okay, again you just let me write it. So, we see first you observe that there is a scale invariance. What does this mean? Let me explain that. So, if u x t is a solution, then u of lambda x lambda square t is also a solution. This easily follows by direct differentiation. So, if we scale the variable x to lambda x, so lambda is a positive number, any positive number, and t by lambda square t, you see that. So, what does this do? So, this x t is there and this lambda x lambda square t is there. So, what is common there? So, if you look at x square by t here, and again I take x square by t here. So, that means lambda x square by lambda square t, and that just gives me. So, the scaling leaves this x square by t unchanged. Okay, this is unchanged. So, that is fixed. Okay, this suggests to look for a solution of the heat equation which is of the form a function of x square by t only, because x, we have seen that this heat equation has this scale invariance, and that suggests us to look for a solution that may not be there, but just we can certainly try that. Okay. So, look for solutions of the form u x t. So, we can even put additional thing here. So, just put a v t and w x square by t. Okay. You do some I have used, let me write that. W is a function of t only and v is a function of x square by t. Of course, this requires we have to only deal with t positive, because we are dividing by t. Now, you just make the necessary differentiations and plug in the heat equation, and so this W and V they satisfy. So, I am skipping few computations. So, I am just using prime, since they are W and V are functions of only one variable. I am just writing prime. Prime means derivative, derivative with respect to the that variable. So, W t for a square v double prime x by t square x, no, sorry, but x square by t x square by t plus v prime x square by t bracket mod x square y mod is not required. We are in the one variable, so just x square by t x square plus b prime x square by t to a square by t. So, remember w and v are at our choice. So, we make first choice. So, choose v such that this term in the bracket is 0. And that immediately gives, so one solution. So, that is a, though it is a second order equation for v, it is a first order equation for v prime. So, you do two integrations and you get one particular solution we take. So, v z is equal to e to the minus z by 4 a square. Okay, that is one solution. And now you plug in this solution v in this thing and you obtain a equation for w prime. So, this is gone and now you differentiate this one and plug in here. So, what you get is, so let me just then w satisfies so you have to work it out. Okay, I am just writing w prime plus 1 by 2 t w equal to 0 and again a particular solution of this first order equation, first order ODE. Okay, remember this ODE. So, this is w t is t to the minus half. So, thus we have obtained a particular solution of the heat equation. So, thus a particular solution of the heat equation is given by u of x t is equal to w t v of x square by t and this one now you replace z by x square by t. So, let me write, since expression in the exponential is big. So, let me write it as exponential. So, this is x square by 4 a square t. A constant multiple of this solution is going to play an important role. So, that is called, so let us put some name. Okay. So, the fundamental solution of the heat equation or heat operator, fundamental solution. is defined by OR operator. Is defined by denoted by kxt so there is a constant multiple here. So 4 pi a square t to the minus half exponential so this is t positive x in R and 0 for a t less than 0. Okay, so what we obtained here, so I am just adding, putting a constant term there. So this 4 pi a square, we will see the reason for putting that particular constant, how that plays an important role. Okay. So immediate observations about this k. So for t positive, exponential is infinitely differentiable, also this t to the minus half. Okay. So immediately just by looking at the expression, k has a singularity at t equal to 0. For t positive, k is an infinitely differentiable function for x in R. And just now we have seen that. Okay. So again for t positive, k satisfies k t equal to a square k x x. So k satisfies the heat equation in the region t positive, and it is a very smooth function, very smooth function. It has only singularity at t equal to 0. Some of them, some profiles of k I can show you. So this is also since this is a Gaussian curve, so it is also referred to as Gaussian. Okay, so it's so as t becomes smaller and smaller, you will notice that the exponential term becomes closer to 1 because t is infinity. So this will become 0. So exponential will become 1, but there is a t to the minus half factor. So as t becomes larger and larger, so we will see that space is less here. So this okay. So this shape, so t equal to t4, t equal to t3 sometimes. Okay. So this is t equal to t2 and t equal to t1, and you drawing x and k. So here T4 is less than T3 less than T2. Okay. So, important thing we will notice that we are going to use that the fundamental solution satisfy the heat equation in the region T positive, that is important, and we will also see that this k is a very smooth function. So, it is infinitely differentiable. Okay. So, these two things will help us in finding a formula for the initial value problem. So, this occurs in the formula for the solution of the initial value problem. Okay. So, anything else? Okay. Yeah. With this we close this lecture, and in the next lecture we will obtain the solution of the initial value problem for the heat equation, and there again we see the role played by this fundamental solution. Thank you.